In this lesson, you will learn how to work with the vertex form of a quadratic function. We will first learn how to identify the vertex from the vertex form, and then we will practice graphing them in vertex form. You will need the graph sheet that was provided to you, as well as a sheet of notebook paper. So let's first start on the notebook paper, just kind of jotting down some notes. The vertex form of a quadratic equation is f of x equals a times, in parentheses, x minus h squared plus k. To identify the vertex from this vertex form, we can take just the h and the k straight from the equation that's in vertex form. So the h, you write down actually what's opposite of what you see. Because it says minus h, the formula is supposed to have a minus sign here. So if you have that, you're going to just write whatever number you see here. We're normally used to seeing this sign and writing down a negative. That is not the case when you name your h. You write down the opposite. So write the opposite. So if we have an equation in vertex form and it says 2 parentheses x minus 4 close parentheses squared, and then whatever is out here to the side. If it says minus 4, we're used to calling that a negative 4, but our h is actually a 4. So you're gonna write down the opposite of what you see. If you see a negative, you write down a positive for that h. For the k value here on the outside, you write down exactly what you see. If you see a plus a number, you write down that number. If you see a minus a number, you're going to take the sign with you. So for the k value, write exactly what you see. So that's how we will identify the vertex from the vertex form. Notice there are no A, B's, and C's like you learned in standard form. So in order to find the axis of symmetry is your H value. So if you want to jot that down, axis of symmetry, X equals the H value. There is no negative B over 2A because we don't have all of those letters in this formula anyways. The axis of symmetry will just be your H value. Let's talk about a few things in this vertex form before we actually start working with any problems. So let's jot it down again. F of x equals a times x minus h quantity squared plus k. Let's talk about what each part of this function does when we're talking about graphing. So the a value will determine whether it opens up and opens down, and we'll talk about that more later. But it also determines if it is a vertical stretch and compression. Vertical stretches and compression. So for example, if we had this equation that was a U shape, that's just the basic U. If we wanted to stretch or compress it, a stretch would be maybe just really tall, where it's taken and really pulled that Y value up very quickly. A compression would be something that it's really flattened it out, really made it squish down. Okay, so that's what that A value does. It stretches it up real tall or squishes it down short. As we've mentioned already, the A value also determines if it opens up or opens down, and we'll look at that some more also. The H value, we do use that to name our vertex, but that will determine a horizontal shift. Horizontal shift. And so that will determine from the origin, is our graph going to shift left and right from the origin? And so you probably guessed it, the K value is going to determine a vertical shift. So that would be up and down. You should have worked with a value a lot like this with linear functions, your plus a b, when you're looking at equations in slope-intercept form. That plus a b can determine if that line shifts up or shifts down. So this k value does that also with a quadratic. Let's go ahead and jot down the notes on the a being positive or negative. You should have looked at this previously with standard form. If a is positive, if a equals a positive number, then the graph is going to open up. You can think about when it opens up, it is pointing in the positive directions. If you think about the y values when graphing, the positive y values are on the top of the graph, so pointing up. This means that the vertex is going to be a minimum. The lowest point on the graph is the vertex, and so that would be why we call it the minimum. And when we talk about domain and range, domain for quadratics are always going to be all real numbers. Those U-shapes will reach eventually every x value that is possibly out there on the graph. But our range is going to be restricted by which direction it opens. So in the case that a is positive, our range is going to be y greater than or equal to the y value of the vertex. So going back to when you named the vertex from your HK, you'll just look at that y value of the vertex. So let's look at when a is a negative. It's going to open down. So think about where the negatives are on a graph. If you graph this on graph paper, the y values that are negative are down. And so that's going to make our vertex going to be a maximum. It's the highest point when it opens down. That vertex is the highest point on the graph, so we call it a maximum. So in this case, we're going to say that our range is going to be less than or equal to, all of those y values are going to be less than or equal to the y value of the vertex. So let's look at some examples so we can begin identifying some vertex values as well as domain and range for these examples. So let's look at number 1. Here we have y equals 2 times x minus 6, quantity squared, minus 7. So notice that this equation is already in vertex form. We can look at our HK to identify the vertex. So recall from the beginning of our notes, when we look at our function, if it says minus h, that's exactly what we need. We need a minus, so you're going to write down the opposite of what you see. I see a minus, so I'm going to write down a positive 6. For the k value, you see the negative 7, you're going to write down negative 7. Write down exactly what you see for that k value. So the vertex of this function is 6, negative 7. If you wanted to think about the axis of symmetry, it would be at 6, that vertical line that cuts the U shape symmetrically in half. If we wanted to think about if this had a maximum or minimum, this vertex, because of the a being a positive, a equals 2, and that's a positive number, this graph is going to open up. So that means that vertex is going to be the lowest point on the graph. So it's going to be a minimum at our y value of our vertex, so at that negative 7. Of course, we talked about domain already being all real numbers. That is always true for quadratics. The range, because our graph opens up, because we have a positive a value, Our range is going to be greater than or equal to, again, the y value of your vertex. So go back and get that -7. We will come back and graph this exact problem so that we can see this to be true in an actual graph. Let's look at example number 2. Here we have y minus 4 equals 7 times x minus 2, and that is all squared. Be careful with problems like this. It's not set equal to y. It looks kind of like vertex form, but because that y is not by itself, we are not actually able to name our vertex just yet. Let's solve for y by adding 4 to both sides. Being cautious that we cannot add the 4 to the 7. That 7 is an a value that is multiplied with this parentheses that's squared. So in order to be able to add the 4 to that 7, it would have to have at x minus 2 squared. So that you can think about these are not like terms in the case of being able to combine them. So when we solve for y, we get y equals 7 times x minus 2 quantity squared, and then we'll just tack on the plus 4 at the end. And that will serve as our k value when we're naming our vertex. So let's do that. Our vertex is our hk. So for h, write down the opposite of what you see. I see a negative, so I'm going to write down a positive. And for k, write exactly what you see. I see a positive, so I'm writing down a positive. So the vertex is hk from our vertex form. Because our a value, go back to where it's solved for y, our a value is 7, and that's a positive number. That means our graph is going to open up. That's going to make this vertex a minimum. And the value of that minimum value, the lowest it reaches down on the graph, is at the y value of your vertex, so a minimum of 4. Of course, the domain will be all real numbers. And our range, again, because it is opening up, we'll have our y being greater than or equal to the y value of our vertex, so 4. If we were to graph this, the range, the y values of our function will go greater than, everything's going to be greater than where our vertex y value was, so at 4. Let's look at another example, number 3. Here we have y equals negative x plus 8 quantity squared plus 1. Try and pause the video to name the vertex and determine if it's a max or min. Let's check your work. So when we're naming the vertex, remember it's the hk of your function. Because this time we see a positive 8, we're going to write down a negative 8. You write down the opposite of what you see for your h value. For the k value, you write down exactly what you see, so a positive 1. So negative 8, positive 1 is the vertex of this function. Because our a value is negative 1, if you need to write in the 1 to help you see that, feel free to do that. Our a value is negative 1. Because that is a negative number, it's going to cause our graph to open down. This time making our vertex a maximum. It's going to be the highest point on the graph. It's going to open down. As the highest point here is that vertex. So to have a maximum value at that positive 1, the y value of your vertex. Of course, again, our domain is all real numbers. Our range is going to be y less than. This time, because our graph opens down, our y values are going to be less than the vertex, so less than or equal to, go back and get the y value again of our vertex, so less than or equal to 1. Let's look at one more example before we start graphing. So number 4. This time we're going to have 14 plus y equals negative 1/2 times x plus 3, all of that squared, plus 8. Of course, always be careful to see first if your graph is, or if your equation is actually in the correct form. This one is not. It looks like it here on the right side. We could say that's our a, h, and k. However, it's not solved for y. This 14 needs to be moved to the other side. So let's do that by subtracting 14 on both sides. Always think about what's going to make it cancel. If you added 14, that's going to make it become 28. Subtracting 14 actually cancels it and gets y by itself. So negative 1/2 times x plus 3 quantity squared, and 8 take away 14 is negative 6. So here we can name our vertex. For our h value, always, always, always be careful with your h. I see several students miss that because they forget the rule of writing down the opposite of what you see. I see a positive, so I'm writing down a negative 3. For the k, write exactly what you see. So here in this case, we have a vertex of negative 3, negative 6. Our a value here is a negative 1/2. We don't really care about the fact that it's a 1/2 right now. We're just looking at the fact that it's a negative. Because it is negative, it's going to open down, making our vertex a maximum value. And that maximum value is going to be at negative 6, the y value of your vertex. Of course, the domain is going to be all real numbers. And the range, this time because it opens down, our y's are going to be less than or equal to, going back and getting the y value of your vertex, so we have negative 6. So now let's shift gears and go and look at our graphing. When we graph these functions, there are two methods, so pick the method that works best for you. So we're actually going to graph the first example. So if you want to recopy that, we have y equals 2 times x minus 6 quantity squared minus 7. We said that our vertex was at 6, negative 7. So the first method for graphing, we'll call it method A, is a lot like graphing quadratic functions in standard form. You find your axis symmetry and vertex. Remember to do that with a quadratic and vertex form, you just name the HK. So this is our axis of symmetry at 6. Our vertex is 6, negative 7. So the axis symmetry and vertex we found by naming our HK, and then we make a table of values. So we can put this vertex in the center of our table, 6, negative 7. It goes in the middle of your table. And if you think about graphing 5 points, the vertex will be in the center. You want 2 points on either side to make that nice U shape. Let's jot down real quick that in case your calculator is not working correctly, how to reset. It's second memory, which is the plus sign, and then you can just use the numeric keys 7, 1, 2. Let me show you what that looks like. So second, this blue key, memory, the plus sign, and then you can just use the numerical keys 7, 1, 2. It's always wise to reset the calculator the first time you use one in case there's any settings that were changed by a previous user that would mess up your graphs. And then sometimes it's just accidentally you have pushed a button that causes it to not do what you think it should. Second, quit will get that screen to clear. And so now we can graph these functions. So we found that our vertex was 6, negative 7, and we need to complete the rest of this table. So in your graphing calculator, you'll hit y equals and type in the function. So 2 times x minus 6, quantity squared, minus 7, being very careful that you type it exactly as the original function, I should say, as the function is set equal to y. Sometimes it won't be the original function. You had to get it solved for y. So once you have your function in y equals, do second table and scroll up and down and see where you can find the 6, negative 7. This is always a good time to do a self-check. If you're not finding 6, negative 7, maybe accidentally you took the exact h value that you see and you wrote down negative 6. Well, if we scroll to negative 6, let's look at that. If we scroll to negative 6, we don't see negative 7 as our y value. So this is a good self-check using the calculator from the start. Did you name the vertex correctly? So we are at 6, negative 7, and we're going to jot down the rest of our y values. So we have 4, 5, 7, and 8 for our x's, and 1, negative 5, negative 5, and 1 for our y's. Notice we should see this repetition. From the vertex, you should see repetition on either side. If not, you are doing something wrong, and so you need to stop and go back and check your work. So let's look at plotting these points. I like to start at the vertex first. So let's go with 6, 2, 3, 4, 5, 6, negative 7, and put a point, and then go to either side of that. You should start seeing the U shape being formed from that graph. So 5, negative 5, 4, 1, positive 1, and then we see these 7, negative 5, so that was 6, so here's 7, negative 5, and then 8, positive 1. I keep wanting to make that a negative 1, so 8, positive 1. So connect those with a smooth curved line. It does make that U shape. You can always go back to the calculator and hit the graph button, and it should give you a graph that looks like your graph. I do not recommend using the graph screen to try and mimic the picture. I see that students usually get off somewhere when they're trying to mimic the screen. Use the second table feature to plot these actual points, and then use the graph to make sure your picture matches that picture of the graph. We've already named the domain and range for this graph from our first example, but we can see that it matches up with the graph that we have now made. The minimum value, the lowest this graph goes, is here at negative 7. The domain is all real numbers. I know we haven't graphed them all, but we could continue on and on forever in both directions. You could scroll in your table and see that. So the domain is all real numbers. Eventually it will reach every single x value. The range for our y values, we said the lowest value was negative 7, and our y values are going to be greater than that negative 7 because it's pointing up. That's why we use a greater than sign. So let's look at method B for this same problem. So again, we have y equals 2 times x minus 6, quantity squared minus 7. We named our vertex to be 6, negative 7. So the way this method is different when graphing is because we're not going to talk about graphing from the origin. When you make the table of values in method A, all of these points are counting from the vertex. So we count 6 down negative 7. We counted 5 down negative 5. So from the vertex is how you graph for method A. For method B, you're going to be graphing from, I said that wrong. This is from the origin. From 0, 0, from the origin from method A. Method B is from the vertex. So how we would do that is we would first start with, go ahead and graphing the vertex first. So graph the vertex. So go ahead and plot the point 6, negative 7. So there's your point for vertex 6, negative 7. Once you graph your vertex, you're going to make an equation. Step 2. You're going to make an equation that is f of x is ax squared to know how to move from the vertex. So our a value was 2. So our equation is going to be f of x or y, you could use either one, 2x squared. This will tell you how to move from the vertex using that a value, because we talked about at the beginning that a is going to either stretch or compress. We've already moved the vertex left and right, up and down the way it needed to go, so now we just need to figure out the stretch or compression with that a value. So this time we want to move one place away from the vertex. So let's evaluate this for 1. So let's plug in f of 1, so 2 times 1 squared. Well, 1 squared is 1, and so 2 times 1 will give us a 2. So this tells us from the vertex, not counting from the origin, go to the vertex and move one x value away and 2 y values away. So starting back at your vertex, one x value away and 2 y values away. And you can go in both directions, one x value and 2 y values away. So that is beginning our U shape, and we see already, because we graphed it with the table, that we are doing it correctly in the right spots. So let's do, and I should have made step 3, evaluate for x equals 1 and x equals 2 moves away from vertex. So that's 1 place away and 2 places away from our vertex. So let's do the 2 places away. So if we do f of 2, we're going to plug in a 2 and square it. Remember, exponent properties first. So 2 squared is 4, and 4 times 2 is 8. So we're moving 2 places away for our x, and 2 times 4 is 8. We're going to move 8 places away for our y. So going back again to our vertex, not the points we just graphed, but from your vertex, move 2 places away, 1, 2 on your x, and 8 places away for your y. 1, 2, 3, 4, 5, 6, 7, 8. And of course it should cause that mirror image, go 2 places to the left this time, and 8 y's. And we see it does make that U shape, connecting them with a smooth curved line. We see that same graph that we got when we graphed it with the table. So pick the method that works best for you. If you like the table, because that's what you did with standard form, and you understood that, and you can just plot the points. Method B is a common way for graphing quadratics, so if you prefer that method, feel free to try it out. You could always do both for a while and always check as you go, and then as you become more confident in one method or another, you can stick with that. Let's look at another example. We're now going to call this example 5, because we're not going to go back and look at any of our other problems. So number 5 here, we have the equation y minus 8 equals negative 3 times x plus 1 quantity squared. So again, be careful if it's not already in vertex form. We might need to solve for y. And in this case, we'll need to do that by adding 8 to both sides. Again, be careful that the plus 8 just goes to the end. It would not combine with this negative 3 because they wouldn't be like terms. So in vertex form, we have y equals negative 3 times x plus 1 quantity squared plus 8. Let's go ahead and talk about all of the pieces and parts of this function. So our vertex will be at our hk. So for h, write down the opposite of what you see. So negative 1. K would be the 8. because our a value, looking here, we're solved for y, this part right here, because our a value is a -3, because that is a negative, it will end up opening down, and we'll see that here in just a moment when we graph it. It's going to make our vertex a maximum at that 8 that we saw for our y value. Then when we talk about our domain, of course it's going to be all real numbers. And our range, because this is opening down, our y's will be less than or equal to that y value of your vertex, so less than or equal to 8. So we'll see that here when we graph it. So let's first start with method A when we graph. This is for problem number 5. So for method A, we're going to put that vertex in the center, -1, 8. So use your graphing calculator to complete the rest of your function. So going back to y equals, of course clear out anything you previously had and type in the function where it's set equal to y. So -3 parentheses x plus 1 close parentheses squared plus 8. Do second table and scroll until you find this xy ordered pair. So -1 in our x column, -1 in our x column, and 8 in our y column. Again, this is a good way to check to see that you named the vertex correctly, because if you would have accidentally said +1, because that's what we see, notice beside the +1 we see -4, so that is not the xy ordered pair for our vertex. Here we see it is -1, 8. So complete the rest of your table. So we have -3, -2, 0, and 1. In our y columns, we see -4, 5, 5, and -4. Again, we see that repetition knowing that we are going to get that U shape when we graph it. We're actually going to hold off on graphing until we do method B, and then we'll come back and make sure they are actually at these points. So for method B, if you prefer this method in graphing, we're going to start with our function f of x, or just y. Let's just use y. Our y is going to be our ax squared. So our a, we said already, was -3, so plug that in. And we're going to evaluate that for 1 and 2, and you could always do 3, but usually getting 5 points, which is 1 and 2 points away from the vertex, will give you 5 nice points to make the U shape. So let's let x equal 1. So if x equals 1, being very careful that you do order of operation, exponents first and then multiply. I do find that some students miss this because they try and multiply first and then square, and that's not what order of operation tells you to do. 1 squared is 1, so -3 times 1, so that gives us -3. So from the vertex, we're going to move 1 x value and -3 y values away. So let's go ahead and plot our vertex at -1, 8. So -1, +8. And let's move as this has just showed us to do. We're going to use 1 x value from the vertex and down 3. So 1 and down 3. Because our y value was negative, 1, 2, 3, we will go down 3. So do the other direction, x being 1 and down 3. Because we've also made the table, we can go and check. That is at -2, 5, so we've just now plotted that point. And that one is at 0, 5, so we just have plotted that point. And of course, we also plotted the vertex. So let's go 2 values away from our vertex. So y equals -3 times 2 squared. We're just evaluating it for this ax squared to see how much it's going to stretch or compress from the vertex. So -3 times 2 squared is 4. So -3 times 4 gives us -12. So we're going to go 2 places away from the vertex on our x, and we're going to go 12 places away in the negative direction for our y. So going back to our vertex. This is where you've got to be very careful, remembering that you're counting from the vertex. You're not counting from the origin. You're not counting from your previous points. You're going always back to the vertex. So x, we're going to go 2 places. Y, we're going to go negative 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think that is correct if I've counted correctly. And then, of course, go the other direction from your vertex, or the other direction. So yes, you can say positive 2. And then down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And check if you want with the table, that is at negative 3, negative 4, and at positive 1, negative 4. So those points also matched up with this method of graphing. So connect them with the smooth curved line, making that U shape. We've already named our domain and range. Our domain is all real numbers. Eventually this graph could keep going and hit every single x value in both positive and negative direction. Our range, if we see our y value here at 8, and our graph went less than that value of 8.